Let me introduce our today's speaker. So, our today's speaker is Vivek Srikumar. He is also my advisor, PhD advisor. And Vivek is an associate professor in the School of Computing at the University of Utah. His research lies in area of natural language processing and machine learning, and is primarily driven by questions arising from the need to reason about textual data with limited supervision and to scale to NLP and to scale NLP to large problems. He has published work at various AI, NLP, and machine learning conferences, and some of these has also recognized with best paper awards, like in Coling and NLP. His work has also is supported by NSF, BSF, NIH, and also several other software companies. Uh, he obtained his PhD from UIUC under Dan Roth in 2013 and his postdoctor from Stanford with Chris Manning. I'm very happy, pleased to host Vivek, and thanks everybody for attending. So if you have any questions and all, I think Vivek is happy to answer in between also. So you can just unmute, don't forget to unmute. And also you can message in the chat, like I have a question, so that if somehow I can also intervene if somebody want to ask a question and say, okay, that person has a question. So if you are not able to intervene in between, so you can also post in the chat. And with this, I hand over to Vivek to start the seminar. And thanks everybody again for coming and attending this session. Thanks.
Cool. Thanks so much. I'm excited to be here because of a few reasons that I'll tell in a minute, but just a matter of logistics. First of all, Vivek, can you tell me if I'm audible?
Yeah, you are audible.
Okay, cool. And the second thing is I can't get the chat window on my screen right now. So if there are any questions on chat, I'm assuming that Vivek will read them out to me.
Yes, I will.
And feel free to interrupt. This is a talk that is really things that I've been thinking about for the last year or so. And it's based on books that I've read recently. And there's definitely some amount of a recency bias in my reading. A recency bias of my reading that has gone into this talk. The title of this talk is it's a reference to this famous book by Martin Gardner. If you haven't read it, it's worth checking it out. It's a book from the 1950s, and it's considered to be one of the first writings about scientific skepticism. Subtitle of the book, in case you can't read it, talks about curious theories of pseudoscience and the strange, alarming, and amusing cults that surround them. A study in human gullibility. This talk is about scientific skepticism, targeting recent work in machine learning and more broadly in artificial intelligence. And so why do we need such a skeptical outlook towards this? Because things seem to be going well. My concern is that things are going a little too well. And there is a constant barrage of news about how well things are going in AI, or how successful things are, that it's a little worrying. Two of these headlines that caught my eye were you cannot spell creative without AI on the top left. And in the middle on the right side, it says, here are 20 dangerous crimes that artificial intelligence will create. A little overblown, I might say. This talk is a skeptical look at recent AI and machine learning advances. And the goal of this talk is, as we are getting into a new academic year and just starting things afresh, I would like to provoke thought and questions and discussions in you and among us, so that we can do fun things as we go ahead. There is definitely some hyperbole in this talk to aid this goal, and please take things I say with a pinch of salt. So with that out of the way, the plan for this talk is I'm going to first talk about the question of whether successful prediction implies understanding. And then I'll switch topics. So the talk is structured as like 3 or 4 sub-modules if you want. Then after talking about prediction and understanding, I'll talk about what I've been thinking in my head as the small data problem. before moving on to how we might be, as a community, uh, subject to a collective illusion of progress. And finally, I'll wrap up with a warning about jumping on the bandwagon. So let's start about understanding. So does successful prediction imply understanding? To kind of set the stage, I want to take you back in time to 585 BC on May 28th, precisely sometime in the afternoon in ancient Greece, in what is today Greece. Something remarkable happened. There was an eclipse, a total solar eclipse, but that's not what the remarkable thing was. The remarkable thing really was that this person, Thales of Miletus, predicted that the eclipse was going to happen before it happened. Otherwise, it's not much of a prediction. But this was one of the first successful eclipse predictions that was recorded in Western history. Most likely, he learned how to do this from Babylonian astronomers who came before him. Now, the question that that I would like us to think about is, did Thales and the Babylonians actually understand how eclipses work? And the answer is actually not really no. He was able to make a prediction about the precise time and location of the totality of the eclipse without knowing a thing about how eclipses work. And there is some evidence that this is true. For example, in this book, there's this quote that says, the recognition that solar eclipses are caused by how the moon and the sun and the earth interact didn't actually come until over a century after Thales of Miletus. Thus, Thales could not have predicted an eclipse in any modern sense. So what he had, one might say, was prediction without understanding. Effectively, using modern terminology, Thales and company, the Babylonian astronomers, data mined celestial observations to find cycles in the lunar and solar eclipses. A popular cycle, for example, is that this is actually a cool observation. If you observe an eclipse, a lunar eclipse today in a certain place, 19 years from today, in the same place, there will be a lunar eclipse. Solar eclipses are a little bit more complicated, but you can kind of make predictions with almost high accuracy. But despite finding these cycles, they had no clue about the positions of the Earth and the Moon and the Sun. In fact, I don't think they even knew that these things were these large celestial bodies flying around in space. This is somewhat similar to what our statistical models are doing today. They find patterns in data that lead to seemingly accurate predictions, but they have no underlying theory. The accuracy in prediction is not because they have an understanding of the phenomena they are modeling, but essentially they're just curve fitting. This is a problem. This can lead to spurious patterns, being the reason for the predictions, and this is a recipe for potential disaster. Let me give you an example. This is the task. Let's use the task of visual question answering to illustrate this. In visual question answering, you're given an image like this image here, and you're asked a question. So, for example, based on this image, you can ask the winning entry from the VQA challenge of 2018. You could ask it, where is the penguin? And the top answer, in fact, the top two answers are saying that the penguin's on the desk. If you're like me and you had trouble spotting the penguin on the desk, it's right here. So this seems amazing. This is this seems remarkable because even a human might miss it, but the program found it. But then you can follow it up, the same system at the same time, or a minute later, you can ask to the same image. You can ask, is there a penguin in the image? And the system says with high confidence, with 100% confidence, no. So now there's a problem. The penguin is on the desk, but there is no penguin, which seems like a weird metaphysical question. What's happening is the system's really devoid of any theory. In particular, it doesn't understand that only one of these answers can be correct. So This is I structured this talk as a series of essentially rants and challenges for you to think about as you go around solving problems for the next generation. The first challenge is what we need are modeling strategies that depend on or expose a theory. By theory, I just mean some underlying understanding of the world that can be communicated to a human. At the very least, we need modeling strategies that assume the existence of a theory. Otherwise, we are basically just finding equations in high dimensional spaces that fit a data set without actually trying to understand what these equations mean, what the data points mean, or what the underlying phenomena are. In some sense, the dichotomy here is Thales, who predicted eclipses using curve fitting, versus a modern view of eclipse science, where we understand the underlying phenomena. So the challenge is, how do we take today's machine learning, which is more on the Thales side of the spectrum, towards something that looks like modern eclipse science? So if you have any questions, this might be a good point to stop. Otherwise, I'll move to the next module. And with the online talks, of course, it feels weird to stop for questions. So if you have any questions, just unmute yourself and ask a question.
I have one question. So how do you exactly know that whether you are going towards the right theory, or you are just fitting things and getting the right answers?
A good theory makes predictions, testable predictions beyond what it was trained on. In science, when we had a theory that said that eclipses are caused by these giant balls of rocks and gas that are floating around in space, if that were the truth, then it leads to other things that might happen. And then the question is, we can run experiments to see if those observations are true. So this is the scientific method. We come up with a hypothesis, the hypothesis makes predictions, and then we run experiments to test the hypothesis. Today, we don't do that with machine learning. We are essentially curve fitting. Now, don't get me wrong, this is actually often how most theories start. But we need to do more.
Okay.
I have another question.
Could you speak up, please? I can't hear you too well.
Hello? How about now?
Yes, much better. Go ahead.
Awesome. So the recent work in explainability, you think that's going to solve this problem or expose this problem?
I hope both. I think the fact that the problem exists is exposed by many recent papers. And explainability is, I think, a fantastic step in this direction. In fact, explainable AI might lead to solutions to this modeling challenge. I haven't kept track of it enough, or nothing has come to my notice that I would argue has solved everything, but it definitely is a step in the right direction. And maybe it can lead to more interesting questions.
I see. Thank you.
And by the way, as I said in the beginning, there's a lot of hyperbole in this talk. When I say nothing exists in the space, it doesn't mean nothing exists. When I say nobody's worked on the space, I don't mean nobody's worked on it. I'm talking about the mode of the community, the most common, the popular things that are out there that most of you in this audience are students, and I'm taking on this deliberately combative perspective, mostly to kind of counter the barrage of social media and news and research papers that you encounter that talks about a certain perspective. So there is some work, for example, in explainable AI, which might already be taking us towards this. And by the way, this is not just in explainable AI today. There was work in the 70s, which kind of went a little too far in the theory side of things rather than curve fitting. And that was its failure. What we need is a mix of both worlds. really we need data-driven methods that can learn to work with the theory that that we are kind of that a human or another system might be guessing, and in some sense we need this sort of a collaborative approach. I don't know what it means to say the theory of desks with penguins on them. I don't know what it means. For maybe that's not the right granularity. Maybe we should not be thinking about pixels as the right abstraction. We need to be thinking about objects, and we need to be thinking about the fact that there is a three-dimensional world and images are just two-dimensional. And I don't know. But this is just, you know, as I said, the point of all of this is to kind of force you to think about these questions so that maybe you'll solve these things.
May I ask a question before we move on?
Sure.
So you said that modeling strategies should depend or expose a theory, right?
Mm-hmm.
But we know that like the world that we are living in is inherently too complex.
Yeah.
We know that like all our, like most of our physical laws, for example, Newton law, breaks down, right, when we go small enough or big enough.
Sure.
So we can only model so much, right?
Yes, that's an absolute truth. We can only, all models are wrong.
Exactly, but some of them are useful, right?
Yes, exactly.
And so there is like, from what I see, that is we should model like as much as it goes, or like to a certain extent, and the rest of it we will try to fit to the data that we observe from the world. So
that is that's how I think about it. Yes.
Okay, so now the question I would like to ask is, how much do you model?
I don't know.
How much do you want to model, and what's the scale? Where do you want to say, okay, this should be modeled, and from now on it should be data driven? Like, where do you draw a line?
That might be a pragmatic choice. That might be a researcher's personality that drives it. There are some people, different people lie on different ends of the spectrum. There are some people who are 100% data driven, no theory, and that seems to be common today. And there are some people who are like 100% theory, no data. I'm going to write programs that just solve it. And this was the 1970s or 60s version of AI. And really the sweet spot is somewhere in the middle. Where exactly, it depends on maybe the problem and the person solving the problem. So for example, let me give you an example of a problem where I feel we should not be using machine learning. Let's say I have two numbers and I want to add them. So the task is you're given two numbers and the goal is to find the sum. Somehow it seems like a waste of computation if we are training a neural network to learn to add when we can just add numbers. We know how to solve the problem. There's no need. The theory of addition is there. So that's a problem where the theory side of things should be complete. But most problems really lie in the noisier side of things. So we need to kind of, when you asked your question, you said, we let the theory go as far as it can and then let the data take over. I think, I don't know which, that implies that the theory comes first and then the data comes later. I don't know if that's necessarily correct. Maybe it is, or maybe they both go together. Maybe the theory is used to guide the learning. So I don't know where the sweet spot is, but it's definitely not at the extreme. So I hope you liked my non-answer there.
Of course, I know it's an open question. There is no like correct answer. So that's why I just wanted to like see.
And it's something to think about. It's just something to think about.
Exactly.
Okay, in the interest of time, I'm going to move on because I see we are at 20-something minutes past the hour. And so let's just move on to the second thing that I'm calling the small data problem. So one might say that, you know, machine learning is data-driven computing, where you have massive labeled data sets, throw it at massive amounts of compute, and we get these massive models that do so fantastically well. As an example of these massive data sets, we have the really popular ones might be things like ImageNet or in computer vision, or FNLI and squad data sets in natural language processing, and really there are many, many more of these data sets. These data sets are painstaking to create. Labeled data is precious and it's very well known. Annotation is expensive. And the way we handle that is we pay people to annotate, for example, on Mechanical Turk or some crowdsourcing platform, or we trick people into annotating things using things like these captchas. One way or another, we get people to do the work for us and build massive data sets. So even when you trick people to do it, there is some implicit payment that's happening. So actually, instead of thinking of machine learning as massive labeled data sets plus these things, notice that both of these things cost money. I'm not going to talk about how compute is expensive and there's a problem there, but you can imagine how expensive it might be to rent a GPU that can load the latest, biggest model that you can think of. So really, machine learning, instead of thinking of it as data-driven.
Vivek, you got mute.
Can you hear me now? Can you hear me?
Yeah, now we can hear you.
Okay. So instead of thinking of machine learning as data-driven computing, it might be appropriate to think of it as dollar-driven computing, because that's how important it is, to do any work. So then the question is it all there is? To solve a new problem, you just need to, throw in a lot of money, create massive data sets, rent the biggest GPU you can find, and solve the problem. And I'm going to argue that there are a whole class of problems where this agenda is not really going to succeed, or at least naively applying this agenda is not going to succeed, and that's why these are going to be challenges. So to give you an example, let me take you to this medieval book called Ball's Leechbook. It's a collection of medical remedies. These are really recipes that are supposed to protect people against things like injuries and infections, but also against things like elves and goblins and devils. It's a curious artifact. There's a digitized version of it in the British Library. This is the page from that collection. And what can it possibly teach us? It seems, other than the fact that it's a curious artifact. So the fact that I've used this particular page in my image, in my slide, is not a coincidence. It's not a random page. In fact, this page, the middle section here, translates into modern English into something like this. It's essentially saying that, to protect against a wen is just an old word for cyst. You mix something like an onion and garlic and wine and bile and leave it for 9 days and 9 nights in a glass vessel, and then you apply it in the night to the eye using a feather, and it's the best medicine. This seems curious, but it makes a claim at the end that this is the best medicine for a certain kind of an infection. So that's a testable claim. It's a testable hypothesis. So two people, Freya Harrison and Erin Connolly, decided to actually recreate this recipe, and amazingly, they found that this particular thing kills modern scourge, namely antibiotic-resistant superbugs, also known as MRSA, which is pretty cool. This is a 1,000-year-old recipe that solves a really modern problem, which has been a pain for modern science. So then the question is, are there other such recipes in this book? Have we, maybe this book contains recipes or remedies for other problems that we are trying to address. Maybe not in this book, maybe in other Old English books, maybe in other books in other languages. Or even more, maybe there are principles of medicine and drug development that we just have essentially lost over the years that we could relearn. Can we build statistical models that can help us with this, that can help us with such drug discovery? Let's think about this last question. What do we need to address that? We need to handle ancient languages and scripts assuming everything is digitized, which is already a problem, but let's leave that to someone else for now. We need to deal with unknown words or ambiguous words, even for things that are familiar. And frankly speaking, most of this book is garbage, like protection from else and such things. So we also need to somehow find what is signal and what is noise. But clearly there is some signal. There's something useful here in this book and maybe in other books. And this is not just a one-off thing. This is not just this cute example that happened to be nice for a slide. This happens all the time. There are many such problems. There was this fantastic book of Dan Jurafsky called The Language of Food, where he read old recipes to trace the spread of culture, of cuisine and language. There are these old undeciphered symbols that exist, and we don't know what they mean, if they mean anything. There are records of these massive records of colonial times, which may contain evidence of colonial brutality, and there are ongoing lawsuits where someone has to read records in a filing cabinet, which essentially amounts to many hundreds of feet of shelves. So we don't measure them in the number of records, but actually feet of shelves. And maybe somewhere there's something interesting. All of these actually have something that we can call a small data problem, which has the following characteristics. These are problems where we don't even know what examples to label. Unlike, say, image classification or such other problems that I showed earlier, we don't even have examples to label because maybe they're hard to find, as in these archaeology cases or these medieval language examples, or maybe they are behind the legal barriers, as in those records or in therapy or in medicine and such things. And even if we found an example to annotate, the person who annotates this example, like annotation is not even the right job, it's analysis. Or annotation is not even the right word here. Each example needs love and care and expertise, which is super expensive. The first problem means we can't forget supervised learning, which is the most popular version of learning today. We can't even use unsupervised learning or semi-supervised learning here. And we can't do crowdsourcing. So somehow these domains and these problems are particularly bad, and they're all over the place. If you start looking, you'll find them everywhere. And often the answer to these problems today is painstaking human labor and human ingenuity. So the challenge is, how do we address such problems using data-driven or statistical methods? One possible way to think about them is we need a very strong inductive bias so that we can get around the fact that there's no data. How do we incorporate such a strong inductive bias? This goes back to this discussion about theories versus being data-driven. Maybe we can transfer solutions from one domain to another, or we can transfer theories that are learned from across problems. And this takes us to these questions of creativity and such things, where the model is no longer just solving a problem or a task or a data set. This is a model of intelligence. So this is another class of problems which keeps coming up, and hopefully I've inspired at least one or two of you to go and solve these problems. This could be another place to pause if there are any questions. If not, I'm going to keep moving on. The third issue that I have, or the third part of this talk, is about what I'm calling an industrial strength blocks world meets metric hacking, which leads us to an illusion of progress. The blocks world, some of you of course know about this, is a famous environment involving simulated blocks, where a user could instruct a computer to move blocks. So a user could say, pick up the red block, and so on. So here's a dialogue between a person, the handler, and the computer. The person says, pick up the big red block, and it says, okay, and it does it. And the person says, grasp the pyramid. The computer says, I don't know which pyramid you mean. And the person says, gives instructions on what it is, and it goes on. So this is an interactive, instructive setting inside the simulated world where you don't get annoying things like friction and feeling thirsty and such things. Anyway, so this was in 1970 roughly. So of course, toy problems are not anything new for AI. These are neat abstractions. There's no real world clutter or noise or flip, and they have a rich history across AI. And of course, other in addition to being popular and important in the development of the field, they also make really good homework problems. So that also makes them nice. They help us understand algorithms, they help us understand domain, and they help us develop new algorithms that can solve hopefully other problems, that can be transferred to other domains. So this was in 1970, and of course, one might think we've moved on from just using toy problems now, but sadly, the fact is it's not true. There is an increasingly popular thing today of using artificially generated data. And the line of thinking goes like this. We need large data sets to train models or to evaluate them. But creating large data sets is a pain. Instead, can I just maybe list out some phenomena that we want to handle very concretely, so concretely that we can write a program that can generate the data set, or maybe does it via simulation. In this case, annotation is free or very cheap. So this is today's version of Block's world. Sadly, these Block's worlds have a very tenuous connection to the real world, as I'll illustrate with one example. I'm just picking this because it's popular. This is an artificial data set called Baby from Facebook AI Labs for reading comprehension. It used 20 focused subtasks where each task was targeting a specific kind of thinking or reading skill, if you want. And for each one, they generated about 1,000 training and test examples. And amazingly, the entire data set with these 20,000 or 40,000 examples was built with a 150-word vocabulary. Just for comparison, a 3-year-old knows more words. An average adult knows a few order of magnitude more words. And yet the paper claimed that this was a step towards AI complete question answering. I mean, of course, in full fairness, it admitted that this was a toy data set and meant to be like a stepping stone. But the thing is, this data set is designed for the tools that we have rather than the problem we want to solve. The tools that we have, namely learning algorithms, demand massive data sets. And as a result, we have this data set. It does not come close to the actual complexity of what reading comprehension or question answering might be. And this has been observed by many papers since then and many authors since then. So just to kind of restate this thing about artificial and real data sets, artificial data sets have a tenuous connection to reality, and maybe the right answer is to always use naturally occurring data sets or create data sets that look like they are natural using humans in the loop. And these are better because they allow us to have a focused discussion about a specific cognitive phenomenon maybe. But unfortunately, doing well on this data set is often misconstrued as solving, quote unquote, whatever solving means, the entirety of computer vision or human vision or language or speech. And this can be a problem. There's a famous quote, the map is not the territory. A data set is an abstraction of a phenomenon that we want to model. It is not the phenomenon. It is finite. almost always in designing the data set, we give up edge cases. We make hard boundaries between what are really soft concepts. The data set is not the task. Doing well on, say, ImageNet does not mean we have solved object recognition. Doing well on a face recognition data set does not mean that we will recognize all faces of all people of all races at all times in all places. So just a few examples of such a data set and a task-driven myopia that has gripped our fields. Computer vision is not the same, as I said, as recognizing these 20,000 objects using ImageNet, or recognizing digits with MNEST, or generating faces, or answering questions about images in any fixed visual question answering data set. Natural language processing is not the same as sentiment. Natural language processing is not the same as natural language inference on a fixed data set, or reading comprehension, or generating word sequences that seem to imply the existence of a mind, but not really. For example, as in these GPT-2 and 3 models do. Of course, all these tasks are an intellectual challenge, but they are not all there is. And this is an important distinction that we should every now and then keep in our minds. Human vision does all of these things that I've listed here and much more. Human language processing does all of this and much more. And what is amazing is that it does all this without actually, we do all this without actually training for these tasks. We don't hopefully ever train children to recognize digits by giving them thousands of digits and asking them to separate them into the numbers 0 to 9. So there's something, this data set driven paradigm is somehow unnatural in itself. But these are the tools that we have, so we should probably live with it. Unfortunately, this approach, this data set driven and task driven, the domination of data set and task driven approaches has actually led to another worrying trend, which involves leaderboards. Essentially, these are fixed data sets with well-constructed experimental protocol, but fixed data set nonetheless, where people can submit the predictions of a model and people are ranked according to how well their model does. The photos I have here on this slide are two popular leaderboards in natural language processing, Claude and Lieu. And if you use the leaderboard as a measure of how well we have understood language, we have done amazingly well. We are like at 90+% performance, according to whatever the performance is on all these tasks. The question though is, has the metric become the goal now? Have we become so obsessed with these metrics that this has become the goal and we have lost sight of the underlying problem there is? And so we have become focused on the data set. Remember, the data set is not the task. And even more strange, weird, or worrying is the fact that most of these systems today apparently do better than humans. I don't know what it means to do better than humans. Does this mean it's fitting the noise in the data? Does this mean that these systems actually can teach the humans what language is, which is kind of strange because language is an explicitly human thing. It's a contract between people about how we communicate ideas to each other. So how is a system that's learning from the data doing better than humans? So, but the problem is there's an obsession with leaderboards across the various applied AI communities. And in all cases, being ranked at the top of a leaderboard, achieving state of the art is a position of pride. But there's something to think about. Even the biggest fixed data set out there is finite. It only accesses a tiny, tiny slice of the cognitive phenomena there are. It only uses a small fragment of the vocabulary that as a collective we are capable of learning. And chasing the state of the art on the leaderboard is counterproductive. Model failures are as important as model successes. So the fact that the system does not get those 8% could mean that the system actually does not have the capacity to get that. And it does not matter how much more data or how much more parameters we throw at the system, it's not going to work. And it's worth thinking deep about what better than human means if humans are the ground truth. So that takes me to challenges 3 and 4, and these are more community challenges in some sense that I feel like we should keep in mind as we approach how we do our own work. Of course, we need data sets to evaluate and maybe even to train models. But how do we teach ourselves to avoid data set myopia? And all of us are guilty of this. Standardizing the evaluation is one of the most important things that happened in the last decade. But how do we avoid this culture of a leaderboard-fueled, state-of-the-art chasing obsession? These are questions to which I don't really have answers other than just asking everyone, including me actually, to every now and then think about these questions so that we don't, we are not only channeled, our thought process is not only driven by data sets and leaderboards. Okay, so I probably have about 10 minutes and just one more thing to say. So are there any questions?
I have, okay, somebody else. Okay, you.
Okay. Okay, so I have a different thinking of the statement that our model has to be trained on millions of data samples, but we as human beings don't need to train on anything of these tasks. But actually, well, that's because our neural networks has been hardwired even before we are born. But this hardwired thing has happened during the millions of years of evolution. So that millions of years can be regarded as a training stage. So actually, our
that's a nice argument. I find that to be very clever, but let me offer you a rebuttal. At no point during the millions and millions of years of evolution, I can assure you this, even though I have no evidence, at no point were we ever trained on reading comprehension. At no point were we ever trained on recognizing digits. We were not trained for tasks or data sets. And I don't even know if we were trained per se. I mean, to be honest, like one of the most insightful papers I've read recently is this paper of Emily Bender and Kohler from ACL this year. When we think of ourselves as learning, as a species or as an individual, we don't learn through just symbols. We learn by interacting with the world. We learn by experiencing the world. And sometimes we learn about things because somebody we trust tells us that it's there. I have personally never seen the planet Saturn, but I believe it's there because somebody I trust told me that. It's a piece of knowledge that is in my brain because someone that I trust actually took the pains to see it. Or there's a chain of trust. So we learn things in so many different ways, and the way we are forcing our models to learn is a supremely narrow channel. And maybe that's not the right way. That's the reason maybe that we are requiring so much data.
Sure.
And I'm not sure that, your argument about our brains having being hardwired to things, I don't know. I mean, I would like to see some evidence of that. Maybe you're right, but maybe it's known, and if you can send me some references, I would be happy to read them. But I don't know.
Okay, thank you.
I have some questions. So one is that you said like these data sets and progress is not real. On the real world, we are not doing this. But there is a counter to that which I want to do is basically because of like the ImageNet and other things, we have made so much progress in vision, and these technology are actually being used by companies all around the world. So our like for example in NLP and other thing like our translations has become better, our speech recognition systems has become
Yes,
better. So
absolutely, yes.
saying that these data set hasn't helped at all won't be like a completely correct statement. And secondly, this is my thought. And secondly, saying that having an artificial data set, I agree that it's not enough to say that we have learned a language or we have learned the task of vision, but it's a good way of probing into things which machine can do and cannot do even. For example, if even I have an artificial data set and I show that the machine cannot even do well on this, where you know the
Yep,
understanding of the, because of the data set you have created or how you have created, you know completely what the task is and everything
sure.
around it. So having doing
So let me, I
yeah.
get your point.
Yeah.
Let me just answer the second question first. You're absolutely right. So for both the questions, the high level point is, of course, there's a lot of hyperbole in this talk. You're absolutely right. Having an artificial data set allows us to probe the limits of models. And if a model can't even do well on an artificial data set, what hope is there for it to do with added noise and such things? But we should not just stop with an artificial data set. We should not stop with just the toy world, because getting 100% accuracy on the toy world with a model that has a billion parameters may be easy. So we should move beyond that. The second thing is, there is no doubt, this is the answer to your first question, there is no doubt that these data sets and this the data-driven paradigm has been immensely successful. Larger data sets have made machine learning possible. Really, larger data sets and more compute is really what it is. But the question that I'm inviting you to think about is, what are the next 20 years of products? Is this the only way to do it? Or is there something else? If all there is to annotate more and more million example data sets, that somehow to me personally seems like a disappointing intellectual effort. Because we are going back to the first point. We are not building an understanding of the world. We are just building an understanding of a data set. I would like to think that AI is more about understanding how the world works.
Okay, completely agree with.
Everything here is, in some sense, trying to make you think about the next 20 years.
Yes, I agree.
Okay, we have 5 minutes left, so about 5. So let me quickly move to the last part of this talk, which is actually completely not mine. I want to talk about jumping on the bandwagon. Let me introduce you to this, if you've not seen this before, a paper by Claude Shannon. Claude Shannon, of course, is it's like one of the intellectual geniuses who shaped the 20th century. His master's thesis, for example, was essentially the proposal that we should use Boolean algebra for digital circuits, which until then nobody had done. And he was 21, and it profoundly changed how we do computing. And not satisfied with that, in 1948, he formalized information theory as we know it. And what happened was, very quickly after that, information theory became extremely widely applicable and really fashionable. In fact, it became so successful that it kind of got into its own little hype cycle, just like machine learning is today. Based on this, in 1956, Shannon wrote a short one-page opinion piece that talked about the dangers of jumping on the bandwagon. It was, of course, focused on information theory, but you can literally do a search and replace in that paper for information theory with machine learning, and you get something that is relevant in 2020. And I highly, highly encourage you to just read this. But what I'm going to do now is walk you through this paper. So Shannon talks, everything that's coming in the next few slides is almost a verbatim quote with minor edits from Shannon's paper. So he talks about the symptoms of the bandwagon. So there's a technical tool, for example, machine learning or neural networks, that starts off as being used by a niche group of scientists and engineers. But it receives an extraordinary amount of publicity in the popular press and also the scientific press, like those examples that I showed in the beginning. And part of the reason for this is because it's connected to a lot of fashionable fields and because it's intrinsically novel. And it unfortunately balloons into an importance that is beyond its actual accomplishment. Fellow scientists, driven by this importance, are pushed into using these ideas, for better or worse, in their own problems. And now this is followed. Shannon follows this with a warning. This wave of popularity carries an imminent danger, carries some danger in it. It is a human tendency to think about these kinds of overarching solutions as a solution for everything. The subject here, information theory in Shannon's case and machine learning for us, is important, but not a panacea. My favorite quote from the paper is in blue here: seldom do more than a few of nature's secrets give way at one time. This artificial prosperity that we have constructed might collapse overnight. When people realize that these new and exciting words, for example, deep learning or generative adversarial networks, or pick your favorite buzzword, they don't solve all problems. What we need is some moderation. We should avoid overstating the relevance of things. Establishing an application of, say, machine learning in a new field is not just trivial translation of words into the new domain. It's a slow and tedious process where we have to come up with hypotheses and verify through experiments. Just because a certain prediction appears to be true in practice, for example, that to use the example that we saw, we can do well on a data set, does not mean that the problem is solved. They must be tested under a wide variety of experimental conditions. There's another aspect to injecting moderation. We need to keep our own house clean. As practitioners of data science or machine learning or applied artificial intelligence, for example, the subject has been sold. People are aware of its existence. We don't need to go around selling the subject. In fact, it's oversold if you believe the media hype. As people who are doing research in this field, we should do our best. We should submit only our best efforts for public consumption. There is a tendency, and it was true in information theory in the 1950s and machine learning today, to keep writing papers. But a few highly well done research papers are better than hundreds of half-done work. The most important point here is we need to maintain a thoroughly scientific attitude, and only this can achieve real progress. With this, I want to take you back to the title of the talk. Martin Gardner, also in the 1950s, wrote about fads and fallacies in the name of science, which talked about scientific skepticism. And that's the attitude I want to kind of want you to think about. This book talks about 60-year-old stuff that, if you read some of this stuff today, it seems funny. So 60 years from now, in 2080, I wonder what people will think about when they think about our work now and find it funny. So just parting words, I want you to think about modeling strategies that expose or depend on some underlying theory. Think about problems where just massive data sets are not going to solve things. Go beyond clean, well-defined toy problems into more dirty domains where we give up on the sort of training wheels. Always question metrics. Metrics are important, but don't be fooled into thinking that your model is fantastic just because it does well on the metrics. Most important of all, beware the bandwagon and be aware that there is one so that we keep ourselves in check. And this is advice not just from me to you, but from me to myself, because we all end up falling into many of these traps. All right, thank you so much for your time. I'll be happy to take questions if time permits. It's 1 o'clock. Technically, we are out of time. So I might stay for a minute or two, and I have to go to another meeting, but you can always reach out. Thanks.
I think
I have a small comment.
Okay.
So first of all, nice talk. So I mean, do you think the information theory was a bandwagon back then? I mean,
If the founder of information theory believed that it was a bandwagon, it's good enough for me.
okay. I mean, considering the sort of the profound impact it has had over computer science in the last 60 years.
I see. I suspect. I mean, since I don't know. I mean, all I know about information theory is what I have seen in classes and few papers that I've read. I suspect there must have been a bandwagon for Shannon to write this, and maybe there were some applications that, I think Shannon's point of that paper was that information theory was being oversold in the media, and maybe there was that. I didn't question his assertion that there is a bandwagon. Maybe there is, maybe there.
Yeah. So I mean, my comment was more aimed at what happened after he sort of.
Oh, sure. Yeah. I mean, of course, it's been an amazing impact. And similarly, there is zero doubt that statistical computing has had an unbelievably outsized impact. So yes, in both cases. But I'm sure everyone has heard of AI winters. So, overselling and overhyping tends to create inflated expectations and a subsequent drop in, say, interest. And so we don't want that.
I think Soumya has one question. She posted. So
Yeah.
Soumya. Yeah.
Hi Vivek,
Hey.
I'm Soumya from ITKGP. Great talk. I had one comment, which was that even when you're learning a new language, you do look at the symbols, you do look at the letters many times, and you sort of train your mind to go through them, right? So that while you're not looking at them probably 1,000 times, but you're still looking at symbols in new letters, which is something that you're technically training your brain to understand.
Sure. Yes. So what's the question?
So this was just a comment. Other than that, I had a question that so while data sets are, and they do give you a myopic view, what I'm trying to understand is data sets also help you tackle the problem bit by bit and sort of chip away at them rather than tackle an entirely large problem which you might have. So if you have a huge problem and you want to be able to tackle it, wouldn't it be good to sort of look at the data set, and then if the leaderboards that you have, the problems over there, the models over there also help you analyze where you're missing, the gaps that you have, and tackle it that way. So I'm trying to understand what a good way to proceed forward
So
over there.
let me actually address the comment that you had about learning from symbols.
Yeah, sure.
I'm not sure we learn only with symbols. We learn through experience. We learn through interactions. We learn through instruction. And if somebody tells me don't touch, so for example, if something is hot and I touch it and I burn myself, I don't need 1,000 interactions to actually learn that. I will be able to generalize that lesson pretty robustly with just a one-shot interaction. So it's not just symbols, but there's some debate on that. We can take that offline. But your second point is about data sets. Yes, absolutely. If a phenomenon is so complicated that like language or vision or cognition or intelligence, how on earth are we going to make any progress if we don't break it down? Divide and conquer is like a perfectly fine strategy. Understanding, comparing different systems on a shared metric in a leaderboard is a perfectly fine thing. What I'm asking is that all there is? Maybe what we should do is, sure, we want to get to the top of a leaderboard, great, But if we have extremely different modeling philosophies, just because we have extremely different modeling philosophies, one of these things might be at the top of the leaderboard and the other one may not. Does this mean that there's nothing to learn from the things that fail? Let me give you a concrete example. Going back to this thing about Thales and the eclipses. At the time when Thales was predicting his eclipse, he could make predictions with remarkable accuracy. Now imagine at that time, someone else came along, and as they did eventually, and said that, you know what, actually these things that are that you're calling eclipses are, I think, because of planets and the moon and the sun being in circular orbits around in the sky. And if these things are aligned in a certain way, we would observe it as an eclipse. And maybe you can run both these tests, both these theories to completion and make predictions. The second theory is going to fail because it's not circular orbits, but elliptical. If we lived in a leaderboard world, that theory would have been tossed aside and never come to the top. And so we need to kind of get back. So we need to learn from failures. We need to not just think of the top system on the leaderboard, but also about the problem. The metric is not the goal, but the problem is the goal, not the data set, not the metric. So while it is imperative that we need to divide and conquer, or at least I can't think of a better way, we need to keep the bigger picture in mind and always keep going back there to see why failures happen and understand if we can learn from the failures. I think there's a question from Nelson, and that will be the last one, and then I'll have to leave. So go ahead, Nelson.
Sure. Yeah. First of all, thanks for such a great talk. I guess my question is kind of similar to Soumya's as well, where it's like, I feel like the first part of your talk was a call to sort of like have a stronger scientific theory of AI. Like we should be building models that depend on like underlying theories. But to some extent, I feel like if we want to do this, it seems like exactly the things that we should be doing would be to look at more toy data sets and like smaller problems. Like, I guess like I'm thinking of how progress in the natural sciences is mostly driven by like toy models. So like, for instance, in biology, you grow things in like petri dishes, and like, sure, that's not a good like I guess approximation for the real world, but it still does teach you something, right? So like, I'm not sure how to square this sort of like need for theory with this aversion to small data sets and to toy.
I think we need both. I think you hit upon a very good example. In biology, you have little experiments, in vitro, in a petri dish, and you might come up with a new, let's say that we come up with a new drug for something. Just because it works in a petri dish, you don't just immediately take it and inject it in a human and say problem solved. There's like a whole phase of tests that you need to run. You go from a petri dish to an animal model, and then you go from there to human trials, multiple human trials. And then, so while it is important that we need these petri dishes to even get started with an understanding of what's going on, it can't be the last thing. It can't be the only thing. So we need to go beyond that, and we need to have this sort of as a community, we need to have this equivalent of this pipeline of going from the petri dish to the animal model, to the human model, to human trials and controlled trials, and being willing to reject a hypothesis at any stage in this process. Just because it works on a petri dish doesn't mean it's going to work on a mouse. Just because it works on a petri dish and a mouse, and because we have spent millions of dollars, doesn't mean that if it fails in a human, it's an acceptable thing. And just because it works on all these test cases, when a drug is eventually introduced in the market, we will assume that it's perfect just because maybe there are some side effects we didn't think about. Right. So at every point, irrespective of how much time, money, and effort has been committed to this particular solution, let's say, we should be willing to give up on our theory. That's what I'm calling for, really. It's scientific skepticism at every level. I don't think any one approach is inherently flawed, but believing that everything is data-driven, believing that everything is curve fitting, or believing that everything is a toy data set, or believing that everything is this one data set that I really like is fundamentally flawed. And so we need to kind of keep going around all of these, in fact.
Okay, right. Thanks.
Hey, I need to go. I'm so sorry, but I'm late
Sure.
for my next meeting.
Sure. So let's have our virtual clap. And thanks, Vivek, for this wonderful and insightful talk, and everybody. And thanks everybody for attending. Yeah. Go ahead.
And I'll be happy to, if any of you are interested in further conversations, send me an email. I'll be happy to chat, because these are things that I really have been spending a lot of time thinking about, and my students know that one way or another I whine about this a lot. So I'll be happy to continue that conversation. All right, thank you so much. I'm going to run, and I'll catch you later.